Hi, my name is Chris, a postdoc and associated member of ML4Q, and you're listening to ML4Q&A. On this podcast, usually members from the Matter and Light for Quantum Computing cluster answer questions about their work in the cluster, their research, and the future of quantum. But in today's episode, I'm not talking to an ML4Q member, but to our first external guest. Steven Koester is a professor of nanotechnology in the Department of Electrical and Computer Engineering at the University of Minnesota. Steve is joining us in his role as the director of the Global Quantum Leap Program, a network of networks, including ML4Q. We talk about his electrical engineering background and how he got a first taste of quantum devices during his master's studies at Notre Dame. This eventually led to a PhD work on indium arsenide. He also gained industry experience working at IBM for 14 years, among other things on silicon germanium. Besides being a professor, he is also the director of the Minnesota Nano Center. But as the main topic, he introduces the Global Quantum Leap Program. The program aims to foster international collaboration and strengthen the link between the fields of nanofabrication and quantum information sciences on an international level. By financing undergraduate internships, ad hoc scientific exchanges and workshops, among other things, it will contribute to the global challenge of realizing a useful quantum computer. All right. It is my pleasure to welcome Steven J. Koester to the ML4Q podcast. You are our first external guest, so it's really an honor. And you come to us from the US, which is even we could have had external guests from Germany, but so this is really, really special.
Yeah, thanks for having me here.
Steve wears many hats. Among other things, he's a professor of electrical and computer engineering at the University of Minnesota. He's the director of the Minnesota Nano Center and director of the Global Quantum Leap Consortium. And that is mainly why you visit us, because this program has a partnership with ML4Q, right?
That's right. And I'm actually here with two students right now who are doing an exchange research project at RWTH.
Indeed. So we should later on, we will definitely talk a lot about the Global Quantum Leap program, how it works, how it relates to ML4Q, and what the opportunities are that it brings. Because I guess for some of the current people in ML4Q, they should also start thinking about it, right?
Yes.
But let's first talk a little bit about you. You're, now you're the director of a quantum program. But you studied electrical engineering. You're not like a physicist by training, right?
I am not a physicist. That is correct.
So we should definitely talk about how you came to quantum physics. I mean, maybe that's a good point to start. So how did you what was your you studied at Notre Dame, right?
Yeah, and so I did my master's at Notre Dame, and then I went on to do my PhD at UC Santa Barbara. And actually at Notre Dame, I got at least a taste of quantum devices, because at that time there was a group of relatively young faculty that decided that they were going to do research on novel electronic devices whose means of operation was some quantum mechanical principle. So, for instance, resonant tunneling diodes was one, and they just wanted to explore that device space as opposed to kind of the conventional transistors. And I thought that was quite exciting.
Yes, indeed. Let's say, indeed, this whole quantum electronics that is becoming a big subject in the early to mid 80s, I think, right? Like there's more, the cryogenic technology becomes more and more available, so the quantum effects become more apparent, and then indeed you run into things like quantized conductance, quantum Hall effect, and things like that, where you can see that electrical conduction is actually quantized.
That's right. That's right. So in my PhD work, that's what I was working on, is looking at quantized conductance in 3.5 materials. It had already been the breakthrough work that was done at Delft, I believe, and in other places on observing quantized conductance in gallium arsenide. And so my PhD research was to do the same thing, essentially, in indium arsenide and indium arsenide aluminum antimonide quantum wells, taking advantage of the larger energy spacings that you could get with the later effective mass of indium arsenide.
Ah, right. So indeed, these material systems, indium arsenide, gallium arsenide, and aluminum gallium arsenide, they all form sort of a building, like a setup where you can play with these properties, right?
That's right. Well, the gallium arsenide is lattice matched to aluminum arsenide, and you can make these gallium arsenide, aluminum gallium arsenide heterostructures. But we were working on, so I was working with the group of Herb Kromer. My advisor was Evelyn Hu, but Herb Kromer's group were the people that grew material for me. And they were working on the indium arsenide, gallium antimonide, aluminum antimonide material system, which creates much larger band offsets. So you can create really large confinement for electrons. And then also indium arsenide has much lighter effective mass, about 3 times lighter effective mass than gallium arsenide. And the idea was that then you could create larger energy splittings of the 1D quantized levels, possibly see these quantized conductance at higher temperatures. And I thought that was interesting because maybe you could make a practical device out of it.
And did that actually pan out?
Yeah, we were able to see the quantized conductance maybe up to about 40 Kelvin or so. Yeah. I think that was better than what had been done in gallium arsenide. Yeah, but it wasn't room temperature or anything like that.
Exactly. Yeah. Taking these effects, I mean, it's possible in some materials to take these effects to room temperature, I believe, but it's very difficult and sort of a niche thing.
Yeah, I think in things some of these metallic break junctions, they've seen quantized conductance at room temperature. It's certainly possible.
Yeah, exactly. It's not theoretically impossible, that's for sure.
Yeah,
it's just hard to do.
That's right. Yeah,
and indeed, already going to liquid nitrogen would make it much more applicable.
That's right. So we were still. I don't think we were turning all the knobs that you could have at the time, but we were just at least taking advantage of the intrinsic material properties.
So how was that for you? We've already discussed, so you had a normal electrical engineering education. When did you learn the sort of basics of why conductance is quantized and so on? How is that process to live at the boundary between the fields?
Well, I mean, I certainly had good teachers. I took Herb Kromer's quantum mechanics class, which was interesting because he taught quantum mechanics for engineers. Yeah. So it was very interesting, actually. He specifically designed a quantum mechanics course for engineers to maybe make it a little bit easier for us to handle and look at a little bit more practical applications. And of course, we learned about Landauer's conductance formula, which isn't too hard to grasp.
It's not so difficult.
It's a simple transmission problem, and so I think the physics, at least for me, was easy enough to grasp, and you could get the basic concepts.
Yeah, I think it's always a very interesting space because, for example, I work in these superconducting quantum circuits, and their electrical engineering is really, really useful. Like a good solid grasp of many electrical engineering ideas really help. And I often feel like I would be probably better at this if I had some electrical engineering classes. So that there's certainly good reasons why, for example, in Aachen and other places, there's more and more joint masters programs where people bring these things together.
I certainly think it helps to have that interaction between the physicists and the electrical engineers. It certainly has benefited me.
Yeah, and I mean the work that you talked about for your PhD, then already you have cryogenics, which is one skill. And it exactly, like, I guess you had to also, like, at the time it was even more manual, so people were still figuring out how to get the electron temperature down.
Yeah, though I did most of my work was just dipping into cryostat at a Dewar. In fact, even dipping in a Dewar at 4.2. We did a little bit of work at lower temperatures, but not a whole lot.
Okay, no, that indeed.
So, but yeah, it certainly was a cross between nanofabrication and material growth. Lots of materials issues with indium arsenide, I can tell you that.
Yeah. Indeed. The growth I guess you weren't the grower, but you did the fabrication. Is that right?
That's right. I worked with collaborators who grew the material, but I did the nanofabrication, the electron beam lithography, and things like that.
So I mean that is also, I mean that it's hard to explain to people, but indeed material growth in itself is usually a PhD, because you need like a year or two to get somewhat good at it, right? And
that's right. And I think that I got my PhD on, I think, basically 3 golden wafers were the ones that I just did my entire PhD on. So.
Exactly, and somebody had to probably grow like 20 or something to get to the right conditions.
That's right. And they were doing their PhD on other things. They were actually doing the collaborators that I worked with were Colombo Bolognesi and Bobby Brar. And they were both doing transistors. So they were making room temperature devices with these materials, but then they would also on the side grow some of these high mobility materials for me.
Yeah, so that and then indeed, like on the one hand, you have these people who work with these growth machines, which is controlling temperatures, pressures, and understanding how things go wrong, which is often really hard.
That's right. And the indium arsenide aluminum antimonide material system was particularly complicated because in the heterostructure, you're actually changing both the cation and the anion. And this creates a lot of issues with how you engineer the interfaces and things like that. So it was quite complex, and there were many PhD theses that were just built on the materials.
And but then you have people like you who then have to take one of these golden wafers and fabricate on them. And I guess like you also didn't have really, really big pieces probably at the time, or was it
2-inch wafer? I had a 2-inch wafer.
They were pretty big actually. That's nice.
I cut those up and I preserved them and protected them with my life.
Yes. So, but indeed, you like, because for the fabrication you have to sort of factor in that it's going to go wrong the first few times, or.
Absolutely, yeah. No, there are many devices, and the worst part is when you say you're almost at the end of your fabrication step and you drop a wafer, or
it's
something
heartbreaking.
Like that. Yeah,
indeed. I think like there's these things where you sometimes you just screw a chip into a plate to clamp it or something, and then the chip breaks in the middle, and right through your contacts or something. Like fabrication is something where you have to have a certain degree of being able to take punishment.
Yeah, and particularly 3-5 materials are very brittle.
Yes.
They cleave very easily.
Yeah. So no, indeed, I feel you. It's and nanofabrication at the time, I guess, was also a bit harder because you still didn't have a machine like our current electron beam lithography machine where you just put a pattern in and the machine writes the pattern.
Interestingly enough, I actually used Santa Barbara had just obtained as a donation an electron beam lithography system called VS1, which I believe was the first generation of the IBM internally developed electron beam lithography systems. And this thing was extremely difficult to use, using very, very old IBM computers and things like that. But it actually served me quite well because eventually I went to IBM and I used some of the same, I actually knew how to use some of this kind of very old software to run these systems. So it was actually benefited me eventually.
But yeah, so what we can take from this is that already in your PhD, you worked a little bit at the interface of nanofabrication, quantum physics, and electrical engineering. That's right, exactly. And then you joined IBM, right? Or you did a brief...
That's right. So unfortunately, I left Santa Barbara after only 4 years. I should have tried to stay there longer, I suppose. Such a nice place. But I then left 1995 and started as a postdoc at IBM, working in their silicon germanium group, and eventually went on to become a research staff member.
Nice. And so essentially you took, how was it? Was a lot of the expertise that you had from the 3-5 materials directly applicable, or?
Well, that was what was interesting, is that I had learned there was I I remember a talk from Khaled Ismail, who was at IBM at the time, and he had come and given a talk at Santa Barbara on these high mobility silicon germanium quantum wells. And eventually that's who I did my postdoc with at IBM. And I just thought that was so cool that you could actually do, a heterostructure in silicon. And that's really fascinating to me. And so I was really happy to go to IBM and start working on these materials.
Okay. So the magic of it, for you, some of the magic of it was just that silicon is the material that powers computers.
Yeah, and it was such a cool technique that you create this relaxed silicon germanium buffer layer and you strain the silicon. Because, at Santa Barbara, we had always just thought that you can't do this sort of stuff in silicon. It was just really something exclusive to the 3.5s. And the fact that you could actually make these really high mobility channels in silicon, I thought was just really, really interesting. And to have the chance to work on it, I think was really exciting.
And indeed, like we can maybe briefly say, actually, some of this, in a way, the quantum dot world, in particular in quantum computing, is sort of very interestingly following this earlier developments. Like early on, you had gallium arsenide also for just 2DECs and quantized conductance, and then sort of silicon following. And in the quantum dots, you also had the early work on gallium arsenide, because everything is a bit bigger.
That's right.
Heterostructures are a bit better maybe and easier to make. And silicon sort of following up.
Yeah, I can see that, yes.
So it's actually quite interesting. Part of your personal path also tracks this development that would later be taken by sort of the quantum community as well.
Yeah, it's kind of interesting that way, yeah.
How was it like? So you came from a university PhD working on sort of fundamental things on electronics, and you joined IBM on a project on silicon, which we all know is a very important material for computer technology. So what were the hopes at IBM at the time, and how did life as a researcher change from the university to the company?
Well, my first 2 years at IBM, I was a postdoc, and so there I got a chance to maybe pretend to be a physicist a little bit. I got a chance to do low temperature experiments and look at low temperature transport in these high mobility strained silicon quantum wells. So we did things like look at weak localization and looking at spin and valley splitting in these materials, and so that was fun. But I think probably later on, I did want to try to look at more practical applications, and of course at that same time there was a big silicon germanium group at IBM. IBM had really been a big pioneer in trying to bring silicon germanium into production technology, originally for bipolar transistors, which actually at that time, or slightly before my time, they were looking at silicon germanium to improve bipolar transistors that were actually used in mainframes. They were actually doing logic with bipolar transistors at that time. But there was also a group that was working on these strained silicon quantum wells, eventually to create a high mobility silicon channel to improve CMOS technology. So there was a lot of activity at that time on trying to explore the practical applications of silicon germanium. And I was anxious to get into trying to be a little bit more practical.
What was the promise compared to CMOS?
So the promise of strained silicon, so this would be, say, a biaxially tensily strained silicon on relaxed silicon germanium, is that it leads to higher mobility. The higher mobility largely is a breaking of the 2 and 4-fold valley degeneracy in the conduction band.
Yes, and the idea is that it's like the higher mobility helps you because of temperature mostly, or what's the like you want, like is it switching? What is the angle? Is it switching time and temperature or?
Yeah. So you'll be able to get essentially faster switching. The metric basically is usually CV over I, the capacitance times the voltage divided by the current. So you can get more current. Your transistors will switch faster.
So indeed, making a faster transistor.
Making a faster transistor, that's right. So the logic switching, you can run at higher clock speeds. This would be the idea. Or you could trade that off to actually operate them at lower voltage, and you could get the same speed at lower power.
Yeah, exactly. That's sort of. I mean, I'm a little bit out of my depth here. I'm very much a physicist and not an expert on computers. But I guess the main things with computers is power consumption, speed of switching, and sort of how small the transistors are and how well you can integrate them.
That's right. Yeah. So that speed and power tend to be traded off against each other. So it creates a better sort of power performance trade-off.
What is the reason why CMOS is still dominating a lot of the technology? Is it the fabrication? Is it ease of fabrication? Because indeed the mobility is not like you can get materials with better mobility and better properties.
Yes, that's true. But for one, as you scale devices, the mobility matters a lot less. So once you're down to a device that has a 20 nanometer channel length, mobility isn't all that important. Mm-hmm. But really, one of the key advantages of silicon is that you can do CMOS. You can do both the NFET and the PFET. So gallium arsenide is great for NFETs, but the PFETs are not very good.
So it's a fabricate. You have one material system where.
Yes, the complementary aspect of it is really, really key. There just really is not another material that can do that.
And the silicon germanium could integrate with some of this, or like can you integrate it with CMOS on the same device, or what is the promise of these kind of technologies? So in the way that we were originally envisioning it, and there were a lot of people that were looking at this, we thought really the best way to get this high mobility in silicon was to strain it, to create a relaxed silicon germanium buffer layer. You would strain the silicon, create tensile strain of the silicon, and then that would be on the surface, and you would be able to enhance the NFET. And theoretically, you're also able to enhance the PFET, the complementary device as well. It actually turned out that you could do that, but it came with a lot of baggage. It came with a lot of other problems. The silicon germanium underneath was defective. It wasn't perfect. So there were a lot of fabrication problems associated with that. It ultimately turned out that silicon germanium was integrated into CMOS, but it was integrated in a very different way. It was integrated in a way where you would put it selectively just in the source and drain contacts of the device, and it would only be in the PFET, in the whole device. And you would create uniaxial compressive strain in the PFET, enhance the PFET mobility, and you wouldn't worry so much about the NFET. You can do some other things with the NFET. So silicon germanium ultimately was integrated into CMOS, but in a very different way than we had originally envisioned. Which indeed, like, let's say the development of computers, you have to try a lot of things that don't work because it's very hard to predict what will. And indeed, fabrication is just it's one thing to have something that works in a university clean room once, and another thing to have something that you put 1 billion transistors of on a chip, right? I guess.
Yeah, and this particular innovation of the uniaxial compressive strain, I think, was actually non-obvious. I don't even know if it had ever been theoretically predicted until the time it was implemented in production. So it was quite a surprise.
Yeah, so indeed, like there's this whole world of people who like you who work on, like, who have a deep knowledge of sort of conventional computer technology. And then there's indeed this physics world. So how long did you stay at IBM?
I was there for a little over 14 years.
And so then you became a professor afterwards, right?
Yeah, so I left IBM in 2010 and joined the University of Minnesota.
And so basically the whole development of quantum technologies starts indeed around like the idea of making quantum dots in 2DECs and using them as qubits. This whole development comes up in the late 90s and and people make the first sort of university level demonstrations on gallium arsenide in the early 2000s, I guess.
I believe that's the case. Yeah.
So indeed, by 2010, people have sort of demonstrated single qubits in gallium arsenide and are slowly so the quantum field is sort of slowly moving from gallium arsenide to silicon for actually not reasons of mobility or fabrication really, but mostly for reasons of the nuclear spins.
That's right, and it's interesting because when I originally joined Minnesota, I wasn't working on silicon germanium anymore, but I certainly was tracking the field, and one of the things that we did in silicon germanium in the early days in these strained silicon quantum wells is we used modulation doping. So we used a phosphorus layer, for instance, to donate electrons into the channel layer, and but that ultimately caused lots of problems for the quantum computing community because of the charge disorder. The random potential fluctuations were just too large from that layer, and so they ultimately started going to the what I would call the enhancement mode types of geometries to get rid of that charge disorder.
Yeah, I mean, well, indeed. So that's I think that's one of the key things that you have the semiconductor world. And for example, I guess the nuclear spins is something that the semiconductor world doesn't think about very much, right? It's like an irrelevant thing.
That's right. There's no isotopic purification that's being done, in standard CMOS. Yeah.
That starts coming in when you take the electron spins and they can see the nuclear spins, and so you arrive at this problem. And this is what makes silicon better, because in gallium arsenide, unfortunately, you cannot isotopically purify a gallium arsenide that is nuclear spin free.
That's right.
Then in silicon germanium, actually you can get there, which is why some people say it's the vacuum semiconductor, because indeed these nuclear spins can be at least for the most part gotten rid of. So that's sort of why the community has slowly moved there. And indeed, a lot of the things, like you said, you worked on the valley splitting. It's sort of an accident of the silicon band structure, right? That you have these valleys. It's sort of.
Well, my understanding, right, is this is kind of a big problem,
yes.
Right? Is being able to make, you need to be able to split this valley degeneracy, and you need to be able to maintain it, in your quantum dot systems.
Yes, because indeed, when you make these quantum dots, you want your electron, and your electron has a bunch of quantum numbers. And in gallium arsenide, it doesn't have this valley quantum number, but in silicon it does. And so you need to, make this quantum number take one value and not any other. Otherwise, you have this electrons in random values.
That's right.
So, and indeed, to engineer this, you have to use things like strain. And that makes things difficult because, indeed, when you have a heterostructure, you have to control strain. There will be defects because, strain almost certainly means that your atomic layers have some sort of mismatch. But indeed, it's about controlling all those things and making it work. And so there's basically by the time that you are a professor, there's already people thinking about these things. So how did you so you left IBM, you became a professor. What is sort of your main research area that you started on and what you're doing now? Because you.
Yeah, my current research is I would say about 75% of it or so is involving 2D materials. So I wanted to start working on graphene and eventually the other 2D semiconductors, mostly because at least with graphene, I just was interested to see what it was good for.
Yes.
There's a lot of hype about graphene, and I thought it was a very interesting material, but I think that at least maybe some of the research directions were not really looking at what the most promising areas of use for it. And so I just wanted to try to explore and see what we could find that would, that graphene could do better than maybe some other, any other material. So now that's not all that quantum related, but it certainly was interesting, and it allowed me to learn a completely new field.
And it's sort of the two deck in one material.
That's right. Yeah, certainly definitely confining electrons and holes to two dimensions for sure.
You also looked a bit like what are the other 2D materials that you have looked at?
So we've looked at molybdenum disulfide, tungsten disulfide. Did some work on black phosphorus, even some work on black arsenic.
The difference being that some of them are more like graphene is not a semiconductor, but I guess a semi-metal, and some of these others are true semiconductors.
Yeah, that's right. All of them have somewhat different properties, and I just think it's really interesting to explore a new material. Once again, trying to figure out what its intrinsic properties are, and then how it could be used for a practical device.
And do you like? So another, like we've already said, you have several hats. You have like a professor where you need to just find good projects for PhD students and be able to have good research output. But then on the other hand, you are director of the Nano Facility. How did you grow into that role?
I mean, I think it's because of my background in nanofabrication. I mean, I started my work in experimental electrical engineering, building an electron beam writer, an electron beam lithography system. So I've just built any number of different types of devices and worked with a wide range of material systems. So after ultimately there was a professor who had been director of our Nano Center for about 20 years or so, and he retired eventually. I feel maybe I was the natural successor just because of my background in so many areas of fabrication.
And how is that role? How many, is it very, is there a lot of administrative baggage attached to it? Is it that you get to, make the big decisions on what to buy, how is it to run a clean room facility?
Well, you got to keep the tools running. You got to make sure that there's DI water and all that sort of stuff. So we have very good staff members that do a lot of that.
Things like cooling water, pumps in the basement, all these things,
air handling, these things. So you have to have all of that done. And once again, we have really excellent staff members that are. I'm so glad that they can make me look so good. But there's also the sort of the scientific aspect of it. You want to try to be getting equipment that will support new research areas, and that's maybe where I've started to get into quantum a little bit. So my background obviously is in microelectronics and in CMOS and conventional computing, and I guess I kind of saw this being the Nano Center director role as an opportunity to think about how do clean rooms need to reconfigure themselves? Do we need to get completely new sets of equipment to support emerging areas like quantum computing? And so that's maybe how I've kind of circled back to look at, to get involved in quantum. Once again, a little bit at the periphery.
Yeah.
Yeah.
And so what is the difference between the clean room needs of a quantum lab and sort of a more conventional classical electronics lab?
Well, that's a little bit of what we're trying to figure out. I mean, maybe it's possible that there are no differences, but I have some suspicion that we do have to, that there might be some specialized tools and techniques that we're going to need. Some things that I can think of would be, being able to control material, the cleanliness of material is much better. So for instance, obviously you have to deal with things like isotopically pure materials. In some cases, you have to deal with magnetic impurities for superconducting devices, making ultra clean interfaces. Do you need specialized tools to prepare interfaces, maybe for things like the topological devices? It's an open question, but I think it's something that we're trying to do, but both in our, me personally, but also within our network of the U.S. network of nanofabs, the National Nanotechnology Coordinated Infrastructure.
Yeah, just indeed. One of the things that I always wonder in this context is I always find that the quantum devices that we make in the end are incredibly primitive, right? Like you have, like, let's say current quantum dot devices. People try to avoid multi-layer fabrication because it induces more charge noise and more problems. So you mostly have, like, sometimes you have some dielectric layers if you really need to cross a gate over another. But if you don't really have to do that, you like in the early devices, you just have like one layer of metal on, let's say a heterostructure, and that's your quantum chip.
That's exactly right, and that could be where there have to be some new techniques developed. So maybe that dielectric layer that allows you to do the crossover metallization has to be deposited in a completely different way than we do it now.
Yeah, I mean, I find it fascinating. Like, if you look at conventional computer devices, I mean, you have many layers, right? Like, and there's steps of polishing and so on, which are also not really done much in the quantum community. Like, we try to mostly do additive fabrication.
That's right. I mean, what we call the back end of the line. That would be all the stuff that's after the kind of the transistor level in conventional computing. It's kind of a dirty process, and it's a question of whether or not you can do that the same way with quantum chips, or you would have to do it in a completely different way.
Yeah, I mean, one of the projects I'm involved with right now, for example, we're looking at whether you can replace some resist-based fabrication techniques with silicon oxide instead, with hard masks, let's say. And that's for example, is a huge question, whether hard masks can be lifted off in a more clean way and leave less residue, whether you can, whether that way you can get device performance improvements or not. And I would say a lot of these questions are not easily answerable. Like,
That's right. And just when you said the word liftoff or lifting off, I mean, liftoff is not a manufacturable process, at least in the silicon world.
Exactly, like this. So the industry works on a completely different way from the way that current quantum dot devices, like current quantum computing devices in the semiconductor world are made, is very, very different from the way that transistors are being made.
That's exactly right. So I find that an interesting question, and by the way, that's just for the silicon quantum dots. If you talk about superconducting qubits or trapped ions, there's all sorts of completely different fabrication issues that come about with that. And
yes.
So, yeah,
indeed. And I think that the US is like it's very, like, having a national network of clean rooms in the US is a really good idea, because these challenges are very important if you want to scale these technologies. I mean, IBM in-house is probably doing a lot is certainly doing a lot at the moment to scale superconducting qubits. Intel is trying to carry scaling of quantum dot qubits to some extent. But like, you really need an interface between these industrial facilities and the universities, and the big clean room centers are probably where a lot of this will eventually happen, right?
Yeah, and I think that at least what we're trying to do is we're trying to bring the community together. So we have what we call a research community within this NNCI network, where we're trying to look at these problems. A couple of years back, we organized a workshop to kind of bring the thought leaders together and discuss these problems, and we're kind of hoping to continue that, just to keep talking about what are the fabrication issues associated with quantum. And you're right, we have to bring in academics and industry and national lab thought leaders, and once again, as well as the international community as well.
So there's a US-based collaboration on bringing the US clean rooms together. Jülich also here plays a role as a hub for nanofabrication for Aachen, Cologne, Düsseldorf, Bonn, like for the universities around here. And then there's a network of networks, which is the Global Quantum Leap, right?
Yes, that's right. So yeah, this is a really unique type of project. So it's funded through the National Science Foundation through a program called AccelNet, which is accelerating research through international network-to-network collaborations. And it's a very unique funding mechanism within the U.S. that really emphasizes international collaborations. This AccelNet program actually funds international collaborations on a whole variety of projects. I think that there's one that is looking at the science of bats, and then also like ice sheets in Greenland. So a very diverse range of topics, but ours is really trying to link the international community on quantum information sciences, and particularly to link the nanofabrication community with the quantum community globally.
Yes, and of course, this is a very good idea. I think we are really lucky as ML4Q to be partnered up, because indeed, so what it does is there's opportunities for research exchange.
That's right. That's right.
This is why you're here, as we already mentioned.
That's right. That's right. So our program, we have a number of different programs that we're running. We have these structured exchanges, which allow U.S. participants to go to any one of our partner sites individually. That's what we're running this year. So this is for undergraduates. So we're sending 3 undergraduates to Hervé Teha. And actually, 3 are going to NIMS in Tsukuba, Japan, as well. So we actually have 6 students this summer. But we also have kind of what we call research-specific exchanges. So these could be exchanges just between 2 of our partners that know each other. So someone in Aachen knows somebody at the University of Chicago, for instance, and they've got a project that they would like to work on that requires a researcher to go to one side or the other, and these are things that we can fund. So we would fund not the research itself, but the connection.
Exactly. So how exactly? Like indeed. So for a lot of our listeners of this podcast are of course within ML4Q itself. It's not that we have a big global audience, but I think specifically for people within ML4Q. What should they have in mind? So if you are a postdoc or PhD student and there's your professor, let's say, finds an opportunity to work with a colleague in the US, what is the kind of procedures what are the possibilities and what would be the procedure?
Right. So they could certainly go to our website, which is globalquantumleap.org. I hope I got that right. So we certainly have a contact email there. We have been posting on occasion specific calls for applications for these research exchanges, but literally anybody can contact us at any time if they have an idea for a collaboration. So some of the structured exchanges we're doing on sort of a regular summer schedule, but any of these research-specific exchanges, literally if there's anybody, if they have a colleague in the U.S. That they would like to collaborate with, that's involving quantum sciences, most likely it's something that we can fund, and we would just like to reach out to us. They can certainly reach out to me at my email address, but also through our website. And we can tell us what idea you have, and then we can talk about how to help to make that exchange happen.
Exactly. So and I think, what we can definitely also say is that learning to like the kind of work, specifically clean room work, is an arduous process because you have to find what works and most things don't. And I think for that, the research visits are really good because any clean room will have slightly different machines, slightly different procedures. And it's absolutely necessary between these clean rooms to have some exchange to actually grow, because, I mean, a lot of the time somebody comes from somewhere else with a certain expertise and then really helps to improve local facilities, right?
Yeah, I think the benefit can come both through the access to some new piece of equipment, but I also think that the benefit can come through a cultural exchange, just thinking about things differently. Sometimes people in different groups just have a very different perspective. They're coming at the problem from a very different angle. And so this idea of just seeing a problem from a different perspective is really beneficial. So kind of get out of your bubble a little bit. And I think that's really, really helpful. And once again, particularly for such a difficult problem as quantum computing.
And indeed, the last thing, of course, sometimes you just need a machine that somebody else has. And I think for a lot of people I would guess that you can probably name some projects where it was really just about finding the capabilities and being well connected. Sometimes you can make things happen much quicker than if you had to buy all the things yourself.
Certainly. I mean, we're dealing with projects that involve very expensive equipment, and sometimes those are unique. There's only maybe one capability within the world.
Yeah.
But once again, I do want to go back to that idea exchange. The being able to just talk to someone that is seeing a problem from a different perspective. I think it just is extremely valuable.
Yes.
And so, I think it's a combination. It's a combination of facilities, people, equipment, and ideas.
And indeed, for the challenge of scaling quantum computing, eventually, because the way that, as we said, the way that current quantum computing devices are, they're relatively primitive fabrication-wise, usually few layers, avoiding a lot of the complicated interconnects, 3D integration, and so on. There's people who move in that direction, but cautiously.
Yes.
Because it's a very big commitment to move into 3D integration, for example.
Yeah, but it's interesting that 3D integration is happening, and I should say that there's a lot of trends in for instance the CMOS industry that is looking promising for integration of for quantum.
Yes.
So there is 3D. There is 3D integration that's being commercialized. We are doing things like removing the dopants from the channel of our transistors, and so a lot of the things that the CMOS industry is doing, they are necessary for quantum, but I don't think that they're going to be sufficient for quantum.
Yes.
And I think that there's going to be more innovations that are needed that go beyond what's currently being envisioned for the conventional computing industry.
Yeah, and indeed. And I think over the next 10, 20 years, as people move from tens of qubits to hopefully thousands of qubits, the fabrication engineering will require a close collaboration with these sort of with the expertise from people who have scaled up computers to billions of transistors.
Yeah, I think that's really going to be important. So I think that having that fabrication expertise is part of the conversation. Once again, particularly as we scale up, I think is really going to be important.
Then just, as we go maybe towards the end of the podcast, I can still ask some more out there questions. Like in this process of managing this this scaling up, certainly at some point, like the current smartphone or computer chips, they require very dedicated foundries that cost billions and billions of euros and are very different from a research clean room. How do we, if we manage that transition, should labs like yours or Jülich, how important is it to get industry partners into research environments or researchers into industry environments?
I think it's going to be important. It's going to be interesting to see how the industry evolves. Of course, it might also have a little bit to do with where the commercial interest lies. How much money do these fabs and the startup companies and things like that, or and the Googles of the world, how much are they really going to be investing in this technology?
Yeah, exactly. If you need to have a dedicated quantum, that's the thing. If you start a startup and you use a university clean room and you pay for it, you need you can pay that from your startup grants and whatever. but if once at a certain size of your quantum startup, maybe you need your own clean room. And at that point, the investment becomes a very different, the amount of money, even for a small clean room, is tens of millions of euros.
Yeah, I really think that in order for this to succeed, it's going to have to be able to use the existing commercial infrastructure. And, there are companies that are supporting some types of, quantum computing. I know that for instance, Skywater in the United States is fabricating these devices for D-Wave. Now, that's not so much, that's sort of a quantum annealing type of process, but they're running a superconducting process. So, I think that, leveraging the existing infrastructure is really going to be important. I don't think that you can have dedicated quantum fabs unless, once again, unless the industry really, unless there's a lot of money to be made.
Another question: in your clean room is also like a research clean room with electron beam lithography mostly.
That's right.
And I mean, of course, the industry works with optical lithography or UV lithography and very advanced mask fabrication, which basically is bad for research, because I guess the kind of masks that people use in advanced semiconductor manufacturing is way too expensive.
Absolutely. I mean, most universities can't even do things like deep UV lithography. To do extreme UV, EUV lithography, it's just absolutely impossible. I think one of the tools might cost, a single tool might cost $50 to $100 million just for the lithography tool. The masks, I just can't even imagine. I don't know how much they cost, but
and they are not easily changeable. That's also it's not that you buy a different mask every week. The e-beam lithography gives you a lot of freedom, I guess.
That's right. I mean, I think that if you wanted to have if the quantum technology is going to require EUV lithography, there has to probably be a very, very large market behind it in order to sustain that. And I don't know that's going to have to come around.
Is there U.S. national labs or clean rooms that do some of this lithography, or is this really something that only is done by commercial?
No, the EUV lithography is done in only a very, very small number of places in the world right now. Okay. Yeah.
Which, and indeed, I've always thought, one of the things that's very lucky about the US is that basically with companies like Intel, the US is a natural part of the value chain of computers, like a lot of the companies there. But I mean, one of the exceptional things in Europe that we do have is ASML, which is kind of a key company for the lithography machines.
Well, and also you have IMEC.
IMEC,
and IMEC is there's quite a lot of work at IMEC on looking at how to build qubits, in a standard,
indeed,
in a standard fab. That's right.
There's a lot of very interesting work coming out of IMEC in the last years for superconducting qubits and also quantum dots, I believe.
Absolutely, yeah.
So yeah, that's so there's things happening in Europe, but the US is certainly more naturally part of the value chain of computing.
I mean, the US has a very robust startup community as well. So there's lots of companies that are getting a lot of venture capital money to look at this. So they're driving it, I think, from the application side. But of course, a lot of still a lot of the advanced fabrication is done in Asia as well. So at TSMC, and so some of that might have to get ported over there, or expanded into the U.S. With some newer capabilities.
Yeah. So I think that we are looking at a very, very interesting time ahead, where people like you have. Are in key positions to help manage, at least help to, if quantum technologies are going to work out, help to make the fabrication side of it happen and transition smoothly into a scaling up process.
I'm hoping at least that's a way that I can contribute. I'm not going to be able to contribute from the physics side, but I do think that there's a lot of manufacturing things to look into that are going to be very important. And so once again, I think this is where the community of physicists and material scientists and engineers need to be able to come together to be able to solve this grand problem.
Yes, and indeed, we're looking forward to it, and we with the Global Quantum Leap, we have a new a way to collaborate with partners in the US very nicely. So everybody in ML4Q should now be aware that if you have ideas for collaborations, you know now where to write to, and we should really all strive to use as much collaboration to facilitate our life, and you know, not wait for the machine to not wait for everything to be available here, but really see where we can work together, exchange ideas, exchange techniques, and make things happen.
Right, I couldn't agree more.
So yeah, thanks a lot for being on the ML4Q podcast, and it was really a pleasure to have you.
Thanks so much for having me.